So I've seen other TechTuber people build out their own Homelab internet service providers. It seems to be kind of a trend lately. I've seen a lot of people do it with dial-up. Dial-up is pretty easy, pretty slow. Someone's even done it with ADSL. Someone even did it with DOCSIS cable. But I haven't seen anyone build their own fiber optic Homelab yet. And so that's what I'm doing today. This is GPON, Gigabit Passive Optical Networking. This is the technology used by major internet service providers to bring internet fiber to the home. FTTX, kind of a buzzword recently. So I'm setting this up right here on my table with my servers in the closet. This is my OLT, my ONUs, my client. We're going to have a good time today. So if you're interested in learning about fiber to the home, passive optical networking, how it's different from traditional active optical networking, etc., then come along on this adventure. Also, big thanks to CData for sending me the equipment to use in this video. More on the hardware later. So now, before I get into the weeds and actually setting up my GPON network, I realize most of you guys probably don't know the difference between GPON and passive optical networking in general compared to traditional point-to-point optical Ethernet or even just basic RJ45 copper Ethernet. So a bit of a primer first. So in the early days of Ethernet, we had a bus. They actually called this the ether. We would transmit frames onto the ether, and anyone could transmit a frame at any time. And they would just go on the ether, everyone would receive them. However, this quickly caused problems, because if two people wanted to transmit a frame at the same time, they would collide and neither packet would get through. So we developed more systems to deal with this. The biggest one was Ethernet switching and full duplex switched Ethernet. So with modern full duplex switched Ethernet, every Ethernet link is essentially point-to-point. We're going from a port on a network card to a port on a switch to a port on another switch, etc. Each of these can transmit frames bidirectionally at full duplex. So we can send frames back and forth, no collisions, and the switch manages collisions using a short buffer. It's called the store and forward method. So frames come into the switch, they get queued into whatever destination they're going to, they go out, everyone's happy, no collisions. So now, if you've done networking, you're probably familiar with how switches work. With optical networking, we can do the same thing, except instead of using copper, we use fiber. We use one fiber for each direction, transmit, receive. We make a fiber link, and we can basically just drop in, replace point-to-point fiber for point-to-point copper. I actually made a video somewhere up here about point-to-point fiber Ethernet, if that's what you're interested in. If you just want to run fiber optic networking around your house, that's the video for you, not this one. So now, if we're running long distance and we don't want to run two fibers, one for each direction, we can use another neat trick of fiber, and that's using different wavelengths, or colors, so to speak. So instead of using one fiber in each direction, we can use one color on the same fiber for transmit and a different color for receive. This is called a bi-die optic, and in the video I linked before, I talk about those as well. And I've actually used those before at my house, where I ran a single fiber to my laundry room so I could fit through a smaller hole where I was pulling the fiber through. But we're still running a fiber between our active switch, where we have a switching ASIC, lasers, things like that, and each customer. So if I'm running a service provider in the city of Flint, I went to university in Flint, by the way, so I'm very familiar with that city. So Flint has about 45,000 houses. I don't know, about 2/3 of them are occupied, maybe 3/4 are occupied. So we'll say if I'm running an ISP, maybe I'm servicing 15,000 houses. And if I have to run 15,000 fibers from every house that I'm servicing back to my headend, and I need 15,000 switch ports, that's a hell of a lot of switch ASICs, switch ports, etc. If I could push those switches out into the field and run less fibers back home, I wouldn't have 15,000 fibers coming into my building. That'd be pretty nice, wouldn't it? Oh, by the way, just let's say on average every run is 3 kilometers, maybe to my headend. So now if I've got 15,000 subscribers for my ISP, and I'm running each of them 3 kilometers back to my headend on average, I need 45,000 kilometers of fiber, which is more than the circumference of the Earth, just for my little ISP in one city. How does that scale? So that leads me on to passive optical networking. Everything I've talked about up until this point we would call active optical networking, because the ends of each fiber are active. We have lasers, we have switching ASICs, things like that. With passive optical networking, we use optical wizardry and magic to split the signal to multiple destinations. So now imagine I've got, say, 64 customers off one fiber. I've got a street's got dozens of houses on it. I run the fiber to the beginning of the street, I split it out to each house. Now I'm running 3 kilometers to the street and, I don't know, maybe a few hundred meters for each house. Much more scalable. So now, if I send a frame down the fiber, it gets split out to all 64 houses. They all receive it. Now that works well. We can use like encryption or something like that to make sure only the correct subscriber gets their frames. But what do we do on the reverse side? What if one of them wants to send a packet upstream? How do we manage that? So today I'm specifically talking about GPON, or Gigabit-class PON, which is an ITU standard, and they use a technology called TDMA, or time slotting, time division multiple access. So essentially what happens here is the headend, the single ISP equipment, gives different slots of time to each customer to send their upload packets. And so if all of the customers want to send upload, they know they're only allowed to send it in a specific time window. And that way, when all of the photons they send out on the fiber meet up in the splitters, they all end up in a nice stream of frames that end up at the headend. So that way we don't have collisions, we can all share data nice and equally and be happy. Now there are some other ways to do this. There are some systems that use a different wavelength for each customer. This might be used if you have like a 10 gig circuit or a 100 gig circuit. You might be using wavelength division multiplexing. This is GPON. This is 2.4 to 1.2 gig. This is the kind of stuff you'd see like for residential fiber customers. So now that we got some theory out of the way, it's time to take a look at the hardware we got. So if I want to start an ISP, all I've got is my uplink connection to the internet, and I guess my client laptop here. What do I need? So in GPON, and PON in general, there's essentially 2 types of equipment we need. So on the service provider side, we need what's called the optical line terminal, or OLT. On the client side, or customer side, we have a device called the optical network unit, or optical network terminal, ONU or ONT. So this guy is the OLT, optical line terminal, I'm going to be using in this video. This is a single port OLT, so it's got one GPON port. Now GPON, despite being called Gigabit-PON, is actually 2.4 gigabit down and 1.2 gigabit up. Now this is probably one of the smallest units you'll see because it's only one port again. Now like a real service provider would probably have a large chassis amount of these things with dozens or so of OLT ports per line card, maybe 8 line cards or something like that. A big setup, but this is a really small setup for really small deployments like mine. So in addition to the single PON port, this guy's got some uplink ports that are traditional Ethernet. This is how we connect it to the rest of our network. So this guy has a single 10 gigabit SFP+. I'm going to be connecting that over fiber to my 10 gigabit switch router in the closet. And I also have 2 gigabit Ethernet ports, which I'm not going to be using, and an RJ45 console. Now for power, I'm just using the AC input, but they also have a 12 volt DC input and an optional battery backup unit. Now you'll notice the PON slot also looks like an SFP cage, and that's because it is. So we need a PON optic that has the right laser wavelengths. In this case, I'm using a class B+ optic. On the far left, we have the status monitor. This shows us basic information like how many ONUs are connected and what kind of bandwidth we're running. Now also, if we wake up the screen, then the unit will start broadcasting out a new Wi-Fi network that we can use to connect to it and manage the unit locally if we're in the building and have messed up our network configuration or don't want to use the console. Also, fun fact, there is so much wavelength available on a single glass fiber that we can carry both traditional GPON, 2.4 gig, 1.2 gig, also XGS-PON, which is 10 gig, 10 gig, the next evolution of this, and also a complete spectrum of cable TV, all on the same fiber to hundreds of customers. So, isn't that magical? So, now that my ISP's got an optical line terminal, I need something for my customers. So my customers probably don't want to plug the PON directly into their laptop, so we need to hand off to Ethernet to them. And that's what the ONU or ONT does. So I've got 3 different types here to look at. All of these are essentially the most basic models on the market. So this guy, he literally costs a few dollars in bulk and ISP quantities. Connect to GPON on one side, get Gigabit Ethernet on the other. Simple as that. This one's a little bit larger. Don't let the size fool you. It's got nothing else going on. It's just got a built-in junction box in the back, so you can run the fiber in, wrap it around, plug it in. They make like a built-in wall box that this can plug onto so it can mount right on the wall and look pretty. And if your customers are more into looks than functionality, and they're in maybe that Unified Bling Club, get them one of these. So this is an SFP module, gigabit, not 10 gig, and it's got the whole ONU built into the end of the stick. For ISPs who want to offer Wi-Fi routers to their customers, CData also has all-in-one units with the ONU as well as Wi-Fi router. If you offer telephone or cable service as well, they have ONUs with triple play. Today I'm just using these 8. These are basic ONUs, so they're just doing Ethernet, not routing, and I should be able to set up 8 clients. So now that I've got my optical line terminal and all of my ISP subscribers have their optical network units, now I got to connect these guys up with fiber optics, valokuitu as we call it in Finland. And for that, I need an optical distribution network. That's a fancy term you'll hear. But first, we're going to take a little bit of a sidebar. We talk about fiber connectors and fiber itself. So, if you watch my past video, probably link up here or something like that, I talked about Ethernet fiber. Now this is like fiber at home, fiber around the farm, that kind of stuff. And I gave you product recommendations you could just plug in and they would work. And it is not that simple to build out an optical distribution network for PON. So for standard Ethernet, we tend to use yellow jacketed cables, which is single mode fiber. Single mode fiber is like the fiber you should be running. People used to use multi-mode because it was cheaper, but you could only do short distances, and now it's just single mode, yellow stuff. So if any of your stuff is aqua or orange, it is multi-mode fiber. If it's orange especially, it's quite old. If it's aqua, it's still modern, but not the best. So then what about the connectors? So for traditional Ethernet, we tend to use the blue connectors. These are unangled polish. So that means that the end of the fiber, it's a stick, there's a ferrule that goes over it, and they polish it flat, no angle. That is the standard for like networking fiber. But for optical distribution networks, we tend to use the green stuff instead. Now this connector is green, but it means that it's been polished at an angle. So the fiber comes up, it's got the ceramic ferrule over, and it's polished on a slight angle. And this means that now we need to line our angles up together, so they have to go in correctly. All of our optical interfaces need to be angled a little bit. But the advantage we get is that we don't get as much reflection back. So if we have a fiber and it hits a connector, it doesn't reflect back and mess up the rest of the distribution network, which is great for PON and for long distance stuff. So for PON, we pretty universally use this little guy here, which is an SC APC connector. So SC is the connector type. It's a single connector because we're using just one fiber now. We're using different wavelengths to go down and up. And then it's APC because it's angled polish. So it's different from the networking fiber here, which is a LC, which is a smaller connector, but we have 2 of them. So an LC UPC duplex connector. So I got my SC APC. But now I can't just plug this in from here to here because I got 3 of these. Maybe I've got 64 of these or something. I need a splitter. So here is the splitter that I bought. The splitter itself is this little tiny silver thing here. This was the cheapest kind that doesn't have like jacketed fibers and stuff. They make them more commonly in like a rack unit with a bunch of ins and outs, or like one in and a bunch of outs. You can also see them sometimes like on a pole. They have like an 8-way splitter they'll put behind a house and run out to each house, stuff like that. So you build a network of these splitters and you try to make a balanced tree. So if I'm going to have 64 customers, I can't just split one fiber into 64. Maybe I'll split it into 4, run that out to the neighborhood, and then each of those 4 can split into 16 or something like that. Maybe I'll do like 8 and 8, so I run 8 and then I split those each into 8 behind houses, something like that. However you do it, you build a network of splits, and each time we split the light, we lose the light intensity. More specifically, each time we split the light in half, we lose half of the light because half of it takes each path. So that's called our attenuation, and we have to figure out how much loss we have in our optical distribution network to get from the OLT to the ONT. So some quick math here. This guy outputs between 1.5 and 5 dBm or decibel milliwatts. This guy needs to receive between -28 and -8 dBm. That means that if I just connect this guy right up to here, I'll have 1.5 going into a maximum of -8. That doesn't work out. So I need at least about 12 decibels of loss. So I need to lose 12 decibels of signal between here and here. So thankfully, I have a splitter. Each time I split it, I lose half, but I'm splitting it not 2 ways, but 16 ways, so I lose 12 decibels. So 3 dB for each half split. I get 4 half splits in this guy, so 3, 6, 9, 12 dB loss. Now this actually came with a test certificate saying 13 dB, so I'm good. But just for the purposes of testing, I've simulated adding a bunch of fiber too. So I've got this attenuator here, the silver piece. This adds another 10 dB of loss, which simulates about 20 kilometers of cable. So that's pretty much on the long end of what you would do for an optical distribution network. So with all that said, let's just hook it up. So before I do the detailed setup of this equipment, we need to know a little bit more theory about how GPON works. Now I've mentioned a couple times in this video that I'm setting up GPON, which is like Gigabit-class passive optical networking, or GPON. But there's also a couple of other standards you might have heard of, specifically EPON or Ethernet PON, and the more recent versions of GPON as well. So GPON evolved into XG-PON, which was 10 gigabit class, and XGS-PON, which is 10 gigabit symmetric class. Many of you probably have XGS-PON if you're using fiber internet at high speeds at home. But GPON is the predecessor to that, and they work the same way. So first off, EPON. EPON was developed by the IEEE. They're the same guys that develop normal Ethernet, IEEE 802.3, wired Ethernet, 802.1, Ethernet MAC layer stuff, and 802.11 Wi-Fi. So those guys know what they're doing. When they developed EPON, it runs at 1 gigabit symmetric, so it's gigabit down, gigabit up, and they essentially used the preamble for the layer 1 Ethernet frame, which is essentially like a 10101010, and it's used to synchronize the receiver in Ethernet. And they robbed some bits from that to encode the station ID. And then they just send the Ethernet frame as normal. So they're still using the time division multiplexing on the uplink, but aside from slightly modifying the Ethernet frame, it's pretty similar to standard Ethernet on the wire. Now you still need special hardware to do EPON, so it wasn't entirely drop-in compatible with the other IEEE 802.3 stuff, but it was as close as they could get it. And that technology hasn't really taken off, I guess. Most of the deployments that have happened in the real world have been of the ITU standard GPON. So I mentioned the ITU. The ITU actually have nothing to do with Ethernet. They're the guys that developed ATM. So if you've heard of ATM or cell switching technology, that works completely differently to Ethernet. So in Ethernet, just like in the olden days where we had the ether, we can send an Ethernet frame at any time. So we just shoot the frame up onto the wire, it gets transmitted. There's nothing blocking it now because we have a point-to-point link, but we don't have to synchronize our frames to anything. We can send them whenever we want. And if we don't have anything to send, we just don't send anything. We leave a gap. But ATM works very differently, and GPON as well. So in ATM, we have a timetable, sort of like, I don't know, like a train station or something. And it says every time slot, we can send this many bytes of data, or frames of data. We call it a cell. And with cell switching, we always have to fill the cell. The cells are always synchronized. We're synchronizing our clocks, so our cells are always aligned in time. This used to be super beneficial in the ATM days when you were sending like real voice calls that came from like a T1 network or something. It's kind of stupid in the modern era, but it's how GPON works. So in GPON, we have the cell stream on the downlink. The uplink cell stream is time division multiplexed. So each transmitter has a certain number of cells they can fill, certain specific cells they can fill. But I'm not doing cell switching anymore. A lot of people aren't doing cell switching anymore. We want to carry Ethernet. We want to carry the modern internet. So in GPON, we create these logical abstractions called gem ports that essentially encapsulates Ethernet on top of the GPON cell switching fabric. So we can send Ethernet frames or parts of Ethernet frames in cell time slots. So from the point of view of everyone connecting to the PON network, this is Ethernet, although it's actually cell switched internally. And of course, we can set up multiple gem ports. If you have like an OLT or an ONU that has like 8 Ethernet ports, you can send a gem to each one individually. There's all kinds of fancy stuff we can do. There's also stuff we can do with multicast. If your provider likes to do like IPTV, for example, you can multicast that over the PON and have that go to every customer. I'm not going to set that up in this video, I'm just doing basic internet, but that's all possible with these gem ports. Now the last thing we have to configure is how much bandwidth we give to each subscriber. Now we don't exactly set this up per gem port, we set this up at a higher level in a container. It's called a TCON. So each TCON contains more than one or more gem ports, and we can set the bandwidth limit for the TCON as a whole. So we could set up a bandwidth limit for each gem port separately if we wanted, or we could merge some of them together in the same bandwidth limit. And this is bandwidth limit on the uplink only. So on the downlink, we can saturate the full 2.4 gig to a single client if all of our equipment supports that. But we want to somehow prevent one user from monopolizing the entire system on the uplink. So what we do on the uplink is the OLT gets to decide what time slots it gives in the TDMA system for each subscriber. And by not giving them very many time slots, they don't get a lot of uplink bandwidth. And so that's how we do like a hard cap on the uplink bandwidth that they can do. Now, like a soft cap, we probably use a queue somewhere else in the system, but that's not part of the PON network. So now let's go ahead and configure these gem ports for our subscribers. So now I'm back here with the GPON setup and we can finally try to configure it. If you're familiar with like an internet service provider architecture, they have a couple of different routers in the system. So the top end, they'll have like their peering routers or transit routers. These are doing eBGP out to their peering customers or peers, their transit upstreams, etc. In my case, I'm just doing this in a Homelab. So I've got my router from my cable company, which is in the closet back here. That's where my internet comes from. So then at the bottom side of the service provider network, we have our connections to all of our individual customers. This is the so-called the last mile, and that's what GPON does here. So this is carrying Ethernet traffic from my data center, where I have the OLT located, to all of my customers, which have their own ONUs. So this is purely layer 2 Ethernet. Now, bridging between this layer 3 IPv4, IPv6 world and the last mile Ethernet, I need a router, and that's called the BNG, the Broadband Network Gateway. So BNG is responsible for terminating all of these layer 2 circuits that go from my data center to my customers, giving them IP addresses over DHCP, providing services like DNS to my customers, also doing stuff like bandwidth limiting and queuing to have a good network experience. This guy doesn't really do queuing, he's more of a layer 2 device. So today, that role is provided by my MikroTik in the closet again. That's my BNG for today. I've also got some virtual machines running on Proxmox that can provide services, such as DNS, for example, and speed test servers we can use. So quick diagram of the whole setup. At the bottom, I have my customers. These are my ONUs from CData. In the middle, I have the optical line terminal. This is also from CData. At the top, I have my IP router, the Broadband Network Gateway. This is my CRS-305 from MikroTik. So that means I've got 2 boxes to configure here today. I've got my BNG, that's got a pretty simple config, and I've also got the OLT, the optical line terminal here, which will be much more of an adventure. So let's dive in. So to start, I'm logged into the OLT here. This is what the web UI looks like. They've also got a CLI, by the way, which you can get to over SSH or the console port. So up at the top, we've got a few different tabs we're going to use a lot. So configuration is where we're going to set up things like the port config, what our uplinks are doing. In this case, I've got one 10 gig uplink. In deployment, we're going to set up all of our common policies that are used between all the ONUs. And then in the ONU tab, we're going to set up each individual ONU if it is anything specific. So in this setup, I'm carrying purely layer 2 Ethernet over the PON. So the PON is not doing any IPv4 or IPv6 routing. That's the job of the BNG. So now I need to isolate all of my circuits to all of my customers and carry that traffic up to the BNG separately, so the BNG can do traffic shaping, logging, etc., whatever is required of the BNG. And so that means I need basically a dedicated Ethernet circuit from each customer endpoint back to the BNG. And on the PON, that's done with GEM ports. But once we get off the PON and we're back on normal Ethernet, we do it with VLANs. So I've set up a whole bunch of VLANs here, one for each customer essentially. So on the BNG, I'll have a VLAN interface that corresponds to each customer. And on the PON here, I'll have a VLAN that corresponds to each customer as well. So I arbitrarily chose VLAN 20 to be like the default VLAN. So if a customer joins the PON and they're not configured, they'll end up there. We could have a splash screen that says like, please call us to configure it, etc., whatever you want to do. But then from there, VLAN 21 and up are my customer VLAN, starting with customer 1 on 21, etc. And basically I can provision these guys through the CLI or through the web UI onto their specific customer VLAN once they've joined the network, or if we know their serial number. So now I've got to set that up here. And the port config is actually fine as it is. I don't have to change anything. But I can come down here to VLAN, port VLAN, and change what VLANs are on which ports. So in this case, XGE is my 10 gig interface. It's configured to have a native VLAN of 1 and tagged VLANs of 20, 30, and 69. So this gives me space for 9 customers. I mean, obviously 9 customers is fine for my little lab here, but you'd probably want like 1,000 of them or something. You do you. And that's super easy to edit. I can just type them in here. I could add 666 or whatever else I want. And over on the BNG, I got the same VLANs tagged, so 20, 30, and 69. And they're on my 2 fiber ports that connect to the Proxmox system and to the OLT. So now I need to get IP service on all of these VLANs so that when a customer connects to it, they get IP. And I just did this all statically in the BNG. Normally you would do this with something like Radius. So Radius can assign VLANs, etc. And probably some config automation as well to automatically create all these VLANs in the BNG. But I've done this manually because I only have a couple clients here. So let's see how this looks. So over here on the router, I've created an interface for each VLAN. So I've got the common customer and then customer 1, 2, 3, 4, etc. So these are the VLANs. So then I need IPv4 and IPv6. So for IPv4, I've got an address like a /24 in each subnet. So 0, 1, 2, 3, etc. These are all in the CGNAT space. And for IPv6, I again have a /64 routing on link. So in theory, if I plug a device straight into this guy, I'll get a 100.64 IPv4 address, and I'll get a globally routable IPv6 address on a /64. This is basically how it should be. So we should be getting our WAN address via DHCP v4 for v4, and via v6 we should have a 64-bit prefix on link, which is what we have, plus like say a /56 available over DHCP prefix delegation, which I also have, but I don't have enough prefix space for those to be globally routable, so those are just temporary. And with that done, we can flip back to the OLT and set up all of the profiles we need. So I'm doing a fairly basic setup today. So I need 3 profiles. I need a DBA profile. This is my uplink bandwidth limit. This is what gives the OLT the ability to schedule uplinks fairly, however it does. I need a line profile, and I need a service profile. So line profile is where we set up the gem ports. Service profile is where we set up all of the VLAN config that we push to the ONU. So these are both important. We can also set up what's called like an auth policy, and this is basically just a container that points to a bunch of other profiles, so you don't have to type in all the different profile names and everywhere. So over here in DBA profile, we have a bunch of options, but the one I'm using today is called DBA Service 100. And so my options here are fixed, assured, assured and max, max, fixed, assured, and max. These are just different algorithms for how to schedule bandwidth on the uplink. So fixed means we always schedule the bandwidth whether we need it or not. Assure means we guarantee they can have up to this much bandwidth, and max means we guarantee they can have no more than this. Normally you would set assure and max for like a residential type profile. If you're doing like IoT stuff where the bandwidth is really consistent, you can use fix, and that'll reduce the amount of scheduling overhead a little bit. So I got assure and max. I've assured 25 megabits and max of 100 megabits. So let's go ahead and confirm that. Now in the LAN profile, I've got Resi 100 again, so this is my 100 megabit service. Also, just to be clear, this is only doing uplink scheduling. The downlink rate limiting is done by the BNG. So the BNG has to do the queuing for the traffic to be like nice. This is more of a hard limit on the OLT when we hit physical limits of what the PON can handle. So anyway, my line profile, I called it Resi 100. It's a VLAN type mapping. I've got one traffic container that's bound to, I can choose what DBA it uses. Then I've got one gem port, and that has a mapping to VLAN 20. We can, of course, add more to each of these. So I could add another traffic container. This could have a different DBA profile, for example. Maybe it's 256 kilobit IoT stuff. And then I can add a gem port on that and a mapping on that. And now this TCONT can have VLAN, I don't know, 21. And both of these are in the system. So if I click TCONT 1, I see the gem port and I see the mapping. If I click TCONT 2, I see its gem port and its mapping. But we'll just go ahead and delete that because I only need one right now. Now these multiple TCONTs, multiple gem ports, are really useful if you're doing like IPTV or segregated traffic. So a TCONT shares the same bandwidth limit because they share the same DBA profile, but you can have more than one gem port in the same TCONT. Now you can also have more than one mapping in the same gem port. So if you want to carry multiple traffics within the same encryption bundle, the gem port, you can do that as well. And finally a service profile. So I have service Resi. So this tripped me up for a while. So first I got to set up what the native VLAN is on each port. So in this case, port 1 is the only port I have, so I've set native VLAN to 20. Then down here I have to set which VLANs are allowed on which port. So in this case, again, port 1 is the only port. I'm setting it in trunk mode, and user VLAN is 20. But I can add another VLAN here. So if I say trunk mode, I could add VLAN 69. Oops, on Ethernet 1. So now Ethernet 1 has access to these 2 VLANs by policy. Last step is the auth policy. Now this is pretty simple. It just lists all the different policies that are part of this greater container. So I've got the line Resi 100 and the service Resi, and I'm not using TR069 or WAN, so we'll confirm that. So now at this point, I should be able to assign ONUs to this profile, and they should just work. Let's try that. So I'm gonna go ahead and change profile here. And let's change him to a policy. We can either pick the profiles individually, or we can say policy, and we'll say Resi policy, confirm. And now it should reconfigure itself. So now I've got a test system here. It's running Kali Linux, which is great if you're doing network analysis. I've hooked it up directly to the ONU and got an IP address. Simple as that. So you can see here I got a v4 and I also got a vfix on link. So we're good. And I can ping. So now to show you what I mean about the uplink bandwidth being limited, not the downlink, let's try iPerf. So I'm going to do an iPerf test as a client to a virtual machine on the system. So we'll go ahead and connect. We're getting about 100 megabits per second, which is what we said was our uplink limit. Now if I run that test again with -R, so I do a reverse direction, now I should get full gigabit down. So 942, etc. That's about the limit of gigabit Ethernet. Gigabit, by the way, is defined by the electrical speed at layer 1, not the packet speed in IP. So we lose a little bit of overhead due to Ethernet framing and due to IP framing. So 942 megabits per second on IP is gigabit on the wire. But now what if I try a bidirectional test? This one's going to be interesting. So I got about 90 megabits on the uplink, but on the downlink I only got about 250, so that's not gigabit. What happened there? So what's happening here is we have two TCP sessions running. We have our upload direction with iPerf, which is one port. We have a separate port, which is downlink. And downlink should be able to send full gigabit, but it also needs to send acknowledgements uplink sometimes. And those are getting dropped occasionally because we're bandwidth limiting so hard on the PON with our DBA profile. So what we really need is a traffic shaping profile that does some sort of better queuing algorithm. And there's some algorithms that are really good, like FQ-CODL, which is particularly designed for service providers. We could run that on our BNG and then set our DBA profile, I don't know, maybe 20% higher than our BNG profile. We also can do traffic shaping in the OLT. So I can do that here in the OLT with the traffic profile. So first I'm going to go to my DBA profile and make him much higher. So we'll say that he's not our limiting factor anymore. We'll just say max of gigabit. And on traffic profile, I need one for downlink and one for uplink. So let's say we're going to allocate him 256 megabit and 512 megabit burst. So we'll go ahead and do that. And for uplink, we'll say the same thing, 6400 and 12800. 64,000 and 28,000. So this should give us 64 megabit up with a peak of 128. So now my line profile, I can edit it, and I can add this to my gem port. So go to the gem port, and we'll say this guy is going to have an uplink bandwidth of that guy, and a downlink bandwidth of that guy. Let's go. So now if I run the BIDER test again, let's see what we got. Yeah, so it looks like we're able to peak at around 128 megabits, and our downlink is best effort about 500. So this is a pretty basic queuing algorithm. You basically set the committed information rate, which you guarantee, and the peak information rate, which you allow it to burst up to, and it fills in the rest. And that seems to work just fine here. Now, if you want to run a more fancy algorithm like FQ-CODL, for example, which is a great one for service providers, you can run it on the BNG also. So looking at the ONU page here, this is the guy I want. So he's ending in E6, E3. I can hit config, and I can override configurations for him specifically. So the last thing I'm going to do specifically is give this ONU a different VLAN by serial number in the config. Now there's probably a way to do this over radius, but again, I have so few ONUs here that it's fine for me today just to hard code this serial number, this VLAN. So here under port config, I can change his VLAN and his VLAN rule. So we can say he's going to be 21 instead, and his user VLAN is also going to be 21 instead. And over here on service channel, we can edit this guy and give him a user VLAN of 21. So go ahead and plug this guy in here, and he should come up and see what we get. So this guy's thinking about life, but if I run IPA, then it looks like I've got an address on a different subnet this time, 2821, and I got no v4, so I'm IPv6 only. So now I can assign different service profiles to different clients, whether some of them have to get stuck with legacy v4, v6 dual stack, or some of them can do IPv6 only, or maybe in the future I could do something like MAP-T, which is something I really want to dig into in the future. But for now I got v6 only, so I can do NAT64 pings. And what do you know? Look at that, it works. Oh, by the way, I also developed Taiga, an open source NAT64 translator. If you want to see the video, hear about it. So that's what I'm using to do NAT64 on my network. I'm working on improving the performance of Taiga along with some other GitHub contributors. So if you're a big fan of IPv6 only networking, which is especially important for service provider networks like this, go ahead and check out that video, or I guess link in the description, something like that. And well, I guess all I have to do now is increase my number of ONUs. So I only got 2, so let's see what a full network setup might look like. So now with more ONUs. This is the biggest setup I have enough equipment to test. So I've got a mini PC here. It's got 4 Ethernet ports, and each one of them is connected to an ONU. Now I know ordinarily you can't just like do this, but through the magic of network namespaces, each of these ports is running its very own namespace, getting its very own routing table, etc. So we can pretend like we have 4 clients. Now I actually don't have enough PCs and power outlets to test with all 8 ONUs that I own, but this is what we can do for now. So I've provisioned 2 of these guys, I don't know which 2, as 200 meg circuits and 2 of them as gigabit circuits. That adds up to 2.4 gig, which is what the PON can handle. So let's see what this looks like on a load balancing side. So you can see here each of these guys appears to have its own IP address. So this guy is 2821, this guy is 2822, this guy is 2823, and this guy is 2824. So we've got 4 separate clients. I can set them each to do an iPerf test to the server. They're going to do 120-second test. And let's go ahead and kick these guys all off. So now a whole lot of traffic should be flowing. So it looks like these 2 circuits on this side are getting about 100 meg up and 200 down. And these guys are getting about 500 up and 800 down. Seems fair. Remember, GPON is not symmetric, so we have 2.488 gigabits down. We only have 1.2 gigabits up. So if I promise 1,000 to all my clients, and somehow all of my clients decide they're going to do gigabit upload at the same time, it's not going to work. Now, in reality, clients don't do this. ISPs have a lot of statistics backing up the fact that they only allocate like 3 to 5 megabits of upstream bandwidth per customer, which may seem wild to you guys that are paying for gigabit, but it's the reality. So it looks like this guy got 200 or 187 down and 93 up. This guy got 181 down, 93 up. These 2 guys over here got like 760 down, 450 up, and pretty much same with that guy. Now I guess that's all I got for today. So this is my Homelab GPON network. Big thanks to CData for sending me this equipment, especially the OLT. Those are trickier to find online. ONUs are not that hard. Hopefully I'll be able to expand more in the setup in the future. Maybe I could go to XGS-PON, or maybe I could do something like RF over glass, running cable over these guys in the same fibers, etc. I have the PLC splitter now, not that it was expensive, but yeah, I like to play more with this stuff, more with fiber in general too. So yeah, if you have any contacts who are interested in sending me that kind of equipment, that'd be great. I have a Discord server linked down below. You guys can chat with me there. I love chatting with people there. I have a Ko-fi. If you want to give me any tips, you can donate there as well. Link down below for that as well. What else? I have a Mastodon. You can follow me there. It's kind of like the Deadbird site, but it's not dead. I guess as always, I'll see you guys on the next adventure.